and welcome to the Calculus Review on Limits. First, we'll be talking about when and why we use limits. Limits can be used to express rates of change, such as velocity. Velocity can be expressed as an average rate of change or as an instantaneous rate of change. In use of limits, we want to focus on the instantaneous rate of change. To find the average rate of change, we use the slope of a secant line. To find the instantaneous rate of change, we use limits. We'll start by defining a limit. The basic definition of a limit. If f of x is defined for all x near c, but not necessarily at c itself, we say that the limit of f of x as x approaches c is equal to L. If the absolute value of f of x minus L becomes arbitrarily smaller when x is any number sufficiently close but not equal to c, we write the limit as x approaches c of f of x equals L. To express the limit of f of x, we can use graphing methods or algebraic numerical methods. When graphing, we will produce a graph of f of x, which can give us a visual impression of whether or not a limit exists. This can also be used to estimate the value of a limit. Numerically, we can make a table of values for f of x for x close to but less than c, and then make a second table of values for f of x close to but greater than c. If both tables indicate convergence to the same number, L, we take L to be an estimate for the limit. Now we'll be discussing two-sided limits and one-sided limits. Two-sided limits are expressed as the limit as x approaches c of f of x is equal to L. One-sided limits are expressed as the limit as x approaches c from the left of f of x, which is a left-hand limit, or the limit as x approaches c from the right of f of x, which is a right-handed limit. If one-sided limits are not equal, then the limit does not exist. One- and two-sided infinite limits. When f of x approaches infinity or negative infinity as x approaches c from one or both sides, we say that the line x equals c is a vertical asymptote. An example of this is the equation in which the limit of 1 over x squared as x approaches 0 from the positive or the negative. This is a visual representation of the graph of this function. The function f of x equals 1 over x squared is positive for all x which are not equal to 0 and becomes arbitrarily larger as x approaches 0 from either side. Therefore, the limit as x approaches 0 of 1 over x squared is equal to infinity. Now we'll be discussing the basic limit laws. Firstly, the sum law. This law states that the limit of f of x plus g of x as x approaches c can also be expressed as the limit of f of x as x approaches c plus the limit of g of x as x approaches c. Now we can talk about the constant multiple law. This law states that for any number k, the limit of k times f of x as x approaches c can be expressed as k times the limit of f of x as x approaches c. Next we'll be discussing the product law. This law states that as the limit of f of x times g of x as x approaches c can also be expressed as the limit of f of x as x approaches c times the limit of g of x as x approaches c. Lastly, the quotient law. If the limit of g of x as x approaches c is not equal to 0, then the limit as x approaches c of f of x divided by g of x is equal to the limit of f of x as x approaches c divided by the limit of g of x as x approaches c. Next, we'll be discussing limits and continuity with Whitney.
Limits and continuity. First, I will define what a function is. A function, f of x, is continuous at x equals c if all of the following conditions exist. Rule number 1. The function has to have value at x equals c. Rule number 2. The limit of f of x as x approaches c has to exist. Finally, rule number 3. The limit of f of x has to equal f of c as x approaches c. Now, the difference between a discontinuous and a continuous function. A discontinuous function has a break or numerous breaks or interruptions within the graph, as you can see here. So, the graph x equals 1, f of 1 equals 0, which is c. So rule number 1, x equals 1 is defined as 0. Rule number 1 is verified. Rule number 2, as the limit approaches 1 from the positive side, x equals 0. And as the limit approaches x from the negative side, the value is 1. Therefore, the limit does not exist because there are two different values for the same input. Therefore, rule number 3 does not work because the limit does not exist. Now, a continuous function. A function is continuous if it has no breaks or interruption within the graph. For example, x equals 1, f of 1 equals 1. So rule number 1, x equals 1 is defined at 1. Rule number 2, the limit as x approaches the positive side is 1. And as x approaches from the negative side, it also equals 1. Therefore, the limit is 1 and exists. Now, rule number 3 can be applied. So f of c is f of 1, which is 1. And the limit of f of 1 as x approaches 1 is also 1. Therefore, f of x equals f of c, and rule 3 is passed. Now, we will algebraically evaluate a continuous function. If the limit of f of x equals f of c as x approaches c is continuous, then the limit can be evaluated by substitution. For example, the function f of x equals x to the negative 2 power. So, the limit of x to the negative second as x approaches 3. 3 is x, so by direct substitution, 3 to the negative 2 power, which equals 1 over 9, which exists. If f of c is not defined, substitution cannot be used directly. For example, the limit of x squared minus 16 divided by x minus 4 as x approaches 4. If we directly substitute 4 in, it will be 4 squared minus 16 divided by 4 minus 4, which equals 0 over 0, which is not defined. Therefore, substitution cannot be used directly. However, the numerator of f of x factors, and then the limit can be evaluated by substitution. By using the previous example, the limit of x squared minus 16 divided by x minus 4 as x approaches 4. Step 1, factor. The numerator can be factored into x plus 4 times x minus 4. And this is all still divided by x minus 4. Step 2, simplify. This gives you x plus 4. The final step, substitute. So the limit of x plus 4 as x approaches 4, you substitute 4 in and you have 4 plus 4, which equals 8. Finally, f of x has an indeterminate form at x equals c if we obtain an undefined expression when f of x is evaluated at x equals c. For example, 0 over 0, infinity over infinity, infinity times 0, or infinity minus infinity. Now, we talk about trigonometric limits and the intermediate value theorem with Laura.
Hi, so we're going to start with the Squeeze Theorem, which assumes that for all situations where x does not equal c in some open interval containing c, L of x is less than or equal to f of x is less than or equal to u of x, and the limit x approaches c of L of x equals the limit x approaches c u of x equals L. The limit x approaches c f of x exists, and the limit x approaches c f of x equals L. So a graph of a function that's being squeezed looks like this. Here, the graph f of x is being squeezed by L of x and u of x at the point where x equals c. Moving on to our first example. Show that the limit x approaches 0, x sine 1 over x equals 0. So our solution. Although f of x equals x sine 1 over x is a product of two functions, we cannot use the product law because the limit x approaches 0 sine 1 over x does not exist. Instead, we can apply the Squeeze Theorem. The sine function takes on values between 1 and -1, and therefore the absolute value of sine 1 over x is less than or greater or equal to 1 for all values where x does not equal 0. Furthermore, if you multiply the absolute value of x by the absolute value of sine 1 over x, you get the absolute value of x sine 1 over x. And the absolute value of x sine 1 over x is less than or equal to the absolute value of x. This means that the negative absolute value of x is less than or equal to x sine 1 over x, which is less than or equal to the absolute value of x, since the limit x approaches 0 of the absolute value of x and the limit x approaches 0 of the absolute value of the negative absolute value of x equals 0. Therefore, we can apply the Squeeze Theorem to conclude that the limit x approaches 0, x sine 1 over x equals 0. So now here are a couple important trigonometric limits which can be proved with the Squeeze Theorem. The first is the limit theta approaches 0, sine theta over theta equals 1, and the limit theta approaches 0, 1 minus cosine theta over theta equals 0. Now on to something a little bit different. We're going to start talking about the intermediate value theorem, which states that a continuous function on an interval cannot skip values, or if f of x is continuous on a closed interval a to b and f of a does not equal f of b, there exists at least one value c within the interval a to b such that f of c equals m for every value m between f of a and f of b. And on to our second example. Prove that the equation sine of x equals 0.3 has at least one solution. So we can apply the intermediate value theorem, which I'm going to abbreviate to the IVT from now on, since sine of x is continuous. We choose an interval where we suspect the solution exists. The desired value, 0.3, lies between two function values, sine of 0 equals 0 and sine pi over 2 equals 1. The IVT, it tells us that sine of x equals 0.3 has at least one solution in the interval 0 to pi over 2. And in fact, it has infinitely many solutions in the interval 0 to pi over 2. Now, a corollary to the IVT. If f of x is continuous on the interval a to b, and if f of a and f of b are non-zero and have opposite signs, then f of x has at least one zero in a to b, in the interval a to b. To locate zeros of functions that are guaranteed by the IVT, we can use the bisection method, which we will do in example 3. So example 3 asks us to show that f of x equals cosine squared x minus 2 sine x over 4 has a 0 in the interval 0 to 2. Then locate the 0 more accurately by using the bisection method. So our solution. Using a calculator, we find that f of 0 and f of 2 have opposite signs, where f of 0 equals 1, which is greater than 0, and f of 2 is approximately negative 0.786, which is less than 0. So the corollary to the IVT guarantees us that f of x equals 0 has at least one solution in 0, 2. We can locate a 0 more effectively by dividing the interval 0 to 2 into two intervals, 0 to 1 and 1 to 2. One of these two must contain a 0 of f of x. To determine which, we evaluate f of x at the midpoint m equals 1. A calculator tells us that f of 1 is approximately negative 0.203, which is less than 0. And since f of 0 equals 1, they have opposite signs. So there is a 0 within the interval 0 to 1. And we can continue calculating this until we know that it is between the interval 3/4 to 7/8 by using this chart and calculating f of x at a midpoint of an interval. Thank you, and that's all for this. Now to summarize. Through this video, we hope that you learn instantaneous velocity, the definition of a limit, two-sided and one-sided limits, basic limit laws, discontinuous versus continuous functions, evaluating limits algebraically, the Squeeze Theorem, and important trigonometric limits, as well as the intermediate value theorem and the bisection method. We have one more question that you should try and do on your own, which is evaluate the limit x approaches 1, x minus 1 over x squared minus 1. Thank you and good luck.